Okay, let's start. So today I will talk about, shall I use microphone? Shall I? Is it better or not? So this is, as I said, we have 5 topics in this course, and now we're getting to topic number 4, which is one-dimensional flows. It is described by differential equations. Let's put it like this. You've seen this kind of equations is in Mass 201, yeah? It's differential equation, simple, first order, autonomous. Who remembers what means autonomous? What's autonomous? Louder? Yeah, correct. We don't have here T explicitly. So non-autonomous would be this. Yeah. And here everything is as it was before. We're supposed to find fixed points or equilibria. Fixed points are root of what? What means fixed point? Fixed point means that our variable is not changing. Variable is not changing means x dot is 0. X dot is 0, since x dot equals to f of x, it means f of x is 0. So this is, roots of this equation are equilibria or fixed points. And same as before, same as for maps, some of fixed points stable, some unstable. There are like Lyapunov stability also, or neutral stability. So all of this applies here, all the same. Yeah, you remember what means stability. If we start at vicinity, if there is a kind of neighborhood of fixed point such that when we start there, we get into fixed point, converge to fixed point, from any point in some neighborhood, then it's stable. If it diverges, it's unstable. If it's neither, so it is not converging but not going away, then it's Lyapunov stability or neutral stability. And these fixed points are roots of this. For example, if x is a fixed point, means f at x equals to x is 0. And your first question in set work 5 is to establish condition when x capital is stable. So in question 1 it's used n instead of x, but it doesn't matter, it's just change of notations. So what we do, we say, okay, let x equal to x capital plus epsilon, something in neighborhood. Epsilon is very small. Yeah. Then if we put it like this, then x dot will be equal to derivative of this. And since this is constant, it will be epsilon dot. X dot equals to epsilon dot. Yeah? Is it okay? Then on the other hand, this should be equal to f of x. F of x, and we replace x by this f of x capital plus epsilon. Is it okay? Do you understand what means epsilon? Epsilon is how much away we are from equilibrium. It's distance from position, local position, to equilibrium. And this will be equal to what we are doing. Do you remember what we do always? What we always do, we use linear approximation. To use linear approximation, we remember what is Taylor expansion and just take two first terms of Taylor expansion. Is it understandable? Yeah? Is it okay? Then we know that f at x capital is 0 because x capital is equilibrium. This condition. Therefore, what we get epsilon dot equals to derivative of f at x capital times epsilon. And this is kind of number, it's derivative at certain point. Yeah? And if this is kind of number, we have linear equation for epsilon. Who knows how to find solution for this? Raise your hands. Yeah. No. It is same as x dot equals to a times x, or dx over dt times ax. You can solve this, yeah? You don't remember? Okay. No, it's good to recall. So this was something pretty much starting point in differential equations. I think you were able to do it in calculus, like in math, at least in math 1 or 2. I will consider this. dx over dt equals to ax, which means we use separation of variables. Dx over x equals to a dt. Then we take integrals of both sides. This integral is easy, it is t plus c. Yeah, c is constant of integration. Agreed? And this integral is, this is logarithm of x. From here we conclude that x equals to, well, I can put it like this, x equals to e to the power of t plus c, which is e to the power of c times e to the power of t. And I can call it a, e to the power of t. So now a should be positive if we have absolute value, but if x is negative, then a also will be negative. So generally, the answer is like this. X equals to a times e to the power of t. And a is value of x at time 0, so what we can put? A equals to x when t equals to 0. I will put it like x now. Therefore, x equals to x naught e to the power of t. So this is a solution for this. Yeah? Do you remember now? It's basic. I mean, all differential equations start with this. And what we have here instead of, where is a, by the way? I forgot a. Here should be a. I forgot about a. I missed a. You didn't correct me. Yeah. I forgot to take a here and it was lost afterwards. So, and if we compare with this and this, we will find out that here should be epsilon as a function of time is epsilon at time 0 times e to the power of a derivative of f at x capital times t. This is our solution. Okay? We have let's put it like this, we made linear approximation for equation for epsilon, and for this linear approximation we found solution. What we can conclude from this solution? From this solution we can conclude, it's like here, what happens to x in course of time? If a is negative, x tends to x tends to 0. If a is negative, tends to, say, infinity if a is positive. And if it's 0, it doesn't change. If a is 0, nothing changes. X always stays the same. Yeah? Do you understand why it and this? Yeah? And here it's the same. Here, if this derivative is negative, epsilon tends to 0. If it's positive, it will grow in course of time. And what does it mean, epsilon tends to 0? You remember that x was equal to x capital plus epsilon. Okay, this is function of time, this is function of time, and this is constant. If epsilon tends to 0, then this x tends to x capital. And this means that x capital is stable. Yeah? So from here we conclude here we conclude, so we don't need this anymore. So from here we conclude that x capital is stable if derivative of f when x equals to x capital you remember that for maps derivative had to be between -1 and 1, yeah, for stability. So this is difference between maps and flows. For flows you compare everything with 0. I think I made a couple of times this mistake. Instead of considering 1 as a threshold, I was considering 0 in a couple of occasions previously for maps, which was wrong, obviously. So here, we should compare with derivative with 0. And what it means, let's put it, now I will put it like this, x dot equals to f of x. And let's say f of x is this kind of, this function, f of x. Can you see here fixed points, and can you tell who is stable, who is not? Anyone? Raise your hands if you can see it. Can you see fixed points? Raise your hands. Yeah. Okay. Can you say, are they stable or not? Which one is stable, which one is not? Okay, good. At least 2 students. So fixed points where function is 0, this, and this. And this is x3. Fixed point is stable if derivative of function at fixed point is negative. It is negative here, it's decreasing, stable. It is unstable. This is stable. Does it make sense? Derivative here is negative, here it's positive, here it's negative. You can put it even different way. Assume you started somewhere here, your x original, x naught is here. Then the f of x is positive. F of x is positive. You remember that x of f of x equals to x dot. Then x dot is also positive. X dot positive means x is increasing over time. Therefore it should go this way in course of time. Does it make sense? If we started here, then f is negative. You see, it's negative. Then x dot is also negative. X dot negative means x is decreasing over time. And you can see that there is convergence for both sides to the equilibrium. Yeah? So this is, it's very illustrative, very easy. As soon as you can see it on this kind of on plots, everything gets straight away. Almost obvious. Here it's the other way around. If we start here, so f for this value is positive, therefore it should increase. X dot should be so positive, x should increase. And here it will need to decrease. It is unstable. You see, there is divergence. And here will be convergence, and so on. Okay, this is pretty much what you're supposed to do. It's more than what you're supposed to do for first part of problem number 1. We can look at problem number 2. Any questions here? Okay. Second part of problem number 1. So we have a law. So I will keep notations. dn over dt equals to minus n squared plus 15n minus 15. And we're supposed to find all equilibrium points, or fixed points. And equilibrium points, their stability, and then we need to find exact solution to integrate it. Okay, let's start with first problem. So f of n is minus n squared plus 15n minus 15. What are roots? Can you tell me? Can you find roots? 10 and 5. So it is minus n minus 5 and minus 10. You can put it like this. Let's plot it. So this is 5, this is 10, it is concave up, so it should be something like this. Yeah? Which one is stable, which is not? How many fixed points we have here? 2. Which one is stable, which is not? 5, stable or not? 10, stable or not? Stable. Yeah. So here derivative is negative, this is stable. Let's put it like this. And capital 1, and capital 2, this is stable. This is unstable. At least this is concerning the first part of story. Formally you could do it, so this is, I used illustration, but you could do it different way. You could say, okay, let's find derivative of n, which is minus 2n plus 15. Then we can say, okay, let's find derivative of n when n equals to 5. It will be minus 2 times 5 plus 15 equals to 5, positive, and therefore unstable. Yeah, so you can do it like this. It's up to you. You can sketch a graph and use it as your argument, or you can find derivative. Derivative of f times n equals to 10 is minus 2 times 10 plus 15 equals to minus 5 negative stable. If you can easily sketch this function, then this seems to be good. If for some reason, if the function is difficult to sketch, to see how it looks like, then you can go this way. Okay, so this is first part of the problem, and second part would be to integrate it. This integration is generally basically unrelated to this model. You're supposed to be able to do it. Anyway, let's try. Let's recap how we do it. So what we have now, dn over dt equals to, I will put it like this, 10 minus n times n minus 5. Yeah, I just put it this minus inside of this. What we do to integrate it? Let's put it like this. Assume you don't know what is anything about fixed points and stability of fixed points, but you nevertheless supposed to analyze solutions of this equation. Then you will try to find exact solution. Yeah, it's an alternative way, it's a long way, it's not always working. You don't expect that you can always integrate differential equation which is given to you. Yeah, but in this case you can. So what is next step? Who remembers? What is next step? It is mass 201. Am I right? Is it correct? Do you remember this? Do you remember this word separation of variables? What it means in this case? So what means separation of variables here? We take n to one side and t to the, we have two variables, n, which is called dependent variable, and t, which is independent variable. So we have two variables, we separate them. It will be dn over 10 minus n times n minus 5 equals to dt. Agreed? We separated variables. What we do next, after separation of variables, now we can integrate it. So the integral of right hand side is easy, it's t plus constant. How we integrate left hand side? Tell me what technique you use. What technique you use to integrate left hand side? Anyone? How it's called? You don't remember how it's called, but you know what is it. Okay. So it's called partial fractions. So this 1 over 10 minus n times n minus 5 can be presented as a times 10 minus n plus b times n minus 5. Yeah, it's partial fractions. What is a and b? Can you find? So if it's 1 and 1, it will be n minus 5 plus 10 minus n. It will be 5 over this. So it should be 1 over 5, I think. It will be 1 over 5 times 1 over 10 minus n plus 1 over n minus 5. Can you check is it correct or not? Yeah? Okay, then the integral of this guy equals to integral of, so I can take 1 over 5 outside. It will be dn over 10 minus n plus 1 over 5 integral of dn over n minus 5. Yeah? What I say, integral of this equals to integral of this. It is what exactly written here. And these two integrals one over 5 logarithm of 10 minus n absolute value. Yeah? You remember this? Plus, I will put it like this, plus logarithm of absolute value of n minus 5. And this was equal to t plus constant. Are you following? Is it okay? Now, next point. Next point, this logarithms my mistake. I made a mistake. What was the mistake? Can you tell me what was the mistake? I made a mistake somewhere. Again. Integral of 1 over 10 minus n dn equals to what? Negative. It will be minus the logarithm of 10 minus n. So here should be minus. Now it will be correct. Yeah. So this, therefore, left hand side will be, well, I can take 5 over there. It will be logarithm of n minus 5 over 10 minus n. Yeah? And this equals to, let's say, 5t plus constant. Since it's constant, well, I can put here 5 if you want. But since it's arbitrary constant, I can just replace it by something else, by c. Okay? And this means that n minus 5 over 10 minus n, but we already did it. It is e to the power of 5t plus 5c, which is equal to a times e to the power of 5. A is e to the power of 5c. Yeah? And then we can remove this absolute value and we will allow for a to be negative. N minus 5 over 10 minus n equals to a times e to the power of 5. So we can come to this. So the only difference is that here a is supposed to be positive, it's an arbitrary number which is positive, but here a can be any number. And how we find a? A is found from the initial conditions. And here it is given. Initial condition n when time equal to 0 equals to 7. It is given in our problem, in statement of the problem. And if n at t equal to 0, what we can do, we can put it like this. So let's put it like this. First, I will put it like this, n naught, whatever n naught is. So if n at time 0 equals to n naught, then n naught minus 5 over 10 minus n naught will be equal to a times, so time should be 0, e 5 to the 0, which is a. And from here we can find what is a, yeah, in terms of n naught. So n naught minus 5 equals to a times 10 minus n naught, therefore n naught plus a n naught will be equal to a times 10. No. So we already found a. We already found a. So this is a. A equals to n naught minus 5 over 10 minus n naught. Therefore we can say n minus 5 over 10 minus n equals to n naught minus 5 over 10 minus n naught times e to the power of 5. So this is what we get. From here we can find expression for n. So this is n is function of time. It is, well, implicitly given like this. We can make it explicit if we want. So we will put, okay, n naught equals to 7 in our problem. Therefore, n minus 5 over 10 minus n equals to 7 minus 5 over 10 minus 7 e to the power of 5t, which is 2 minus 2 over 3 e to the power of 5t. Yeah? And from here we can put like this. N minus 5 equals to minus 2 over 3 e to the power of 5t. 10 minus n. N minus 2 over 3 e to the power of 5t. N equals to 5 minus 2 over 3 e to the power of 5t. And from here we can take n outside of brackets here. Let's put it like this. And therefore n will be equal to 5 minus 2 over 3 e to the power of 5t over 1 minus 2 over 3 e to the power of 5t. Hopefully I didn't make any mistake. Minus 2, 3. I think it's correct. So I think I made a mistake in my solution. Convinced. Now the question was what happens to n? This is n is function of time. What happens to n when time tends to infinity? I think something I made a mistake somewhere probably, but I don't see.
Should it not be positive 2/3 and so on?
Is this correct?
The bit where you're doing n minus 5 over 10 minus 7 should not be positive 2/3 and negative 2/3.
7 minus 5 or 10 minus, this should be positive. This should be positive. Okay, one mistake. If this is positive, it is good. And here should be plus. And here should be also plus. This is plus and this is plus, yeah? Explicit solution in my solution is different from what I put it here. Why? So the question is this correct or not? So this is correct. It's 2 over 3 e to the power 5t. It is correct. And but n minus 5 goes out. Here is plus. Again?
5 plus 20 over 3 e to the power
5, just a minute. This is what I forgot. This 5 should be multiplied here, it will be 10 here. This was my mistake. Yeah. Because it should be 5. Where it was? It is 20 over 3. So this was correct. N plus 2 over 3 e to the power of, this is correct, equals to 20 over 3 e to the power of 5t plus 5. So here was a mistake. And therefore, n will be equal to 20 over 3 e to the power of 5t plus 5 over 1 plus 2 over 3 e to the power of 5t, and it tends to, when time tends to infinity, it will tend to, if time tends to infinity, this tends to infinity, this tends to infinity, we can neglect this and this, it will tend to 20 over 3 e to the power of 5t divided by 2 over 3 e to the power of 5t, which equals to 10. Yeah? And we remember that 10 was stable fixed point. Okay, so we did first problem. We have 10 minutes to talk about problem number 2. Do you have any questions? Okay, problem number 2. So problem number 2, it is next class of problems, and this is probably the main subject, the main point in section 4. It is about equations with parameters. We had equations with parameters all the time generally. This logistic map was already mapped with parameter. And when we have parameter we consider bifurcations. Why we consider bifurcations when we have equation with parameter? With parameter. So what we have, x dot equals to f of x and subdivided c. Now, fixed point depends on value of parameter, and its stability also depends on value of parameter. So let's put it like this. F of x c equal to 0 is fixed points, and derivative of f when x equals to fixed point c defines stability. And what the main point about bifurcation is that if we change our parameter a little bit, for example, we made our analysis for certain value of c. If c is changed slightly, then pretty much everything is the same. So our fixed point will change position slightly, but its stability probably will not change. So we don't expect it is one of main points in math. That if you have a parameter and you slightly change parameter, then generally you don't expect big changes in your solution. Otherwise it would be nightmare. Otherwise you couldn't trust anything. Because for applications, we write some equation, and in this somehow we presume that there are some kind of stationary environment, and therefore many things are assumed to be fixed constants. But then you don't expect that if some environment temperature changed a little bit, or like atmospheric pressure changed a little bit, then everything dramatically will change. So generally it will be pretty much the same as before. It is coming to the point I made on the first lecture, when you measure something, you don't have absolute value. You always have value measured with certain accuracy. So it could be slightly different compared to what you assume. And if it's even slightly different, whatever you got is still okay, fine. But there are exceptions from this rule, indeed. And these exceptions, they called bifurcation values for parameter. So generally, if you change your parameter, everything is fine. But there are exceptional cases when you slightly change your parameter and everything gets different. What exactly gets different? Two things can get different. Number of fixed points and stability of fixed points. And eventually this, so for maps, we remember then that you get a fixed point, and at this fixed point, if eigen, let's for one-dimensional case, if derivative of your function at fixed point equals to 1 or minus 1, it is places where you expect some changes, bifurcations. Yeah, because, for example, if you have a fixed point, when it changes stability only when absolute value of derivative at this fixed point goes from the range minus 1, 1 to outside. Yeah? And eventually, so this is about stability, but eventually when fixed points appear or disappear, they always appear or disappear when this derivative at fixed points, at this fixed point which appears or disappears, equals to 1 or minus 1 also, generally. Well, I mean, if we consider complex eigenvalues, real lambda, imaginary lambda, so it is on the border. So here this is stable. outside is unstable, and all bifurcations is if lambdas are real, then these 2 points we consider imaginary part is 0. But if it's also imaginary, then all this border is place where our bifurcations can take place. Yeah, it is for maps. But if we consider flows, then even this I plotted, you see, so they can be complex for two-dimensional maps. For one-dimensional map, it would be line. So here it is stable, because you have, it is derivative of your function, it is real number. For two-dimensional, we consider these eigenvalues of lambda. You see, I always get from one topic to another in some disorder. So this is for 2D maps, and this is for 1D map. And for 1D flow, we consider, so this is derivative of x. So this is 0. So here is stable, here is unstable, and here you have bifurcations. Bifurcations always associated when with the case when derivative of function, of this function, at fixed point is 0. Yep. And from here we can already conclude how to find bifurcation points. We don't, so I'm not talking about what kind of bifurcations we will have, but to find, so a bifurcation points are two conditions. F of xc is 0, it is fixed point, and derivative of f over x at xc is 0. So this is condition for bifurcations. Bifurcation point, yeah. If these two conditions met, then we can have bifurcation. It's not guaranteed that there will be bifurcation, because as you remember, for example, eigenvalue can come here and then turn eventually instead of passing, then we will not have bifurcation. But if we have a bifurcation, these two conditions should be satisfied. Okay, this is about bifurcations, and now we can talk about this problem number 2. So in problem number 2, we have differential equation with parameter. So what we have is y dot equals to 3y, y minus 10 minus c. So let's try to plot it. So let's do it easy. Let's first consider case c equal to 0. If c equals to 0, we can plot it straight away. Yeah. Then we have two roots. C is 0, it disappears. So this function is 0 when y is 0 and y is 10. So here and here two roots, and it is concave. brown, it should be something like this. Agreed? Yeah? Now, if C is not 0, but something positive, what happens to this curve? It will go up. Minus C goes down here. So here C positive, and therefore C negative will be something like this. And you can already see, can you see when we will have bifurcation? We have two fixed points, this and this. If C is decreasing, this curve is going up, 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 and at some point it will just touch. These two fixed points will merge at some value of C. And so then if C is further decreasing, we will have no fixed points. Yeah, so if C is less than C star, we will have no fixed points. If more than C star, we will have two fixed points. So this is place when number of fixed points changes. And this is bifurcation. Yeah? Okay. And maybe we can stop it now here, because it's our time, 9:52. So I will continue from this point to on Monday. Okay, questions?